Okay, good afternoon all. We have successfully completed Wave Characteristics 1 and polarization, concept of polarization and the concept of pointing theorem. And the last topic here, electromagnetic wave characteristics 2. In this, we are going to consider two mediums. So one, it is like a boundary conditions. One is two mediums are two dielectrics with different properties. Another one is medium one is a dielectric, medium two is a conductor. So here you see that heading, normal incidence at the boundary interface. Interface means in between the two mediums, the junction point is a interface. So whenever the wave is passing from one medium to another medium, that point joining point is called interface. Now normal incidence means incident wave, the electromagnetic wave, whenever it is going to be strike somewhere, it is called incident wave. So for this interface, it is perpendicularly incident, that is called normal incidence at boundary interface. Okay. Now this concept is similar to in our transmission lines concept. Okay. Now, if we consider this concept of transmission line, we have a transmission line. The transmission line has a characteristic impedance of Z0. Now, suppose the line is terminated with ZL. Now, whenever the Z0 is equal to ZL, so the line is properly terminated. Whenever the line is properly terminated, whatever the wave is incident at the load, so whatever the wave is incident at the load, the total wave is absorbed by the load. There is no any reflection taking place on the line. Similarly, if you consider another case, whenever the Z0 is not equal to ZL, Z0 is not equal to ZL. So what happens? Z0 is not equal to ZL. Definitely, there is a reflection taking place. Reflection taking place on a line. So the similar fashion here, we are going to consider two mediums, medium 1 and medium 2. Suppose if we consider two dielectric mediums, the first medium has its own properties, second medium has its own properties. So if we calculate intrinsic impedance, already we have seen for a phase space, for a perfect dielectric, for loss dielectric, for a good conductor, we have calculated these intrinsic impedances. Now, whatever we are going to consider the two mediums, medium 1 has intrinsic impedance eta 1 and medium 2 has intrinsic impedance eta 2. So there is a impedance is not matching. So it is like a transmission line. In the transmission line, the characteristic impedance is equal to ZL, so there is no any reflection. Here also, the medium 1 intrinsic impedance, medium 2 intrinsic impedance, both are same. There is no any reflection. But whenever these two are not same, definitely some part of the wave is reflected back into the same medium. Some part of the wave is transmitting to second medium. So that is the concept. Here we are going to discuss about three waves: incident wave, reflected wave, transmitted wave. Transmitted wave means at the boundary surface, at the interface of the boundary between the two mediums, the EM wave is passing from medium 1 to medium 2. Okay? Bhagasri?
Sir.
You got it?
Yes, sir.
Okay. is the concept is similar to your transmission line concept. So we know the concept of reflection very well. So the reflection, when the reflection is possible on a transmission line, whenever characteristic impedance and load impedance are not same, characteristic impedance and load impedance are not same, then there is a reflection taking place. Here also, whenever we are considering two mediums, the two mediums maybe two are the dielectrics with different properties, and one medium is a dielectric, another medium is a conductor. You know, we have seen in a dielectric medium, in a free space, there is no any losses taking place. So it is a lossless medium. Free space is a lossless medium, and perfect dielectric is also lossless medium. So for a dielectric medium, the conductivity is zero. Whenever the conductivity is zero, attenuation is zero. Whenever attenuation is zero, the medium is a lossless medium. So whenever any medium offers some conductivity, definitely there is some loss is going to be taking place. So that is some attenuation is taking place. So totally the wave is going to be attenuated somehow. Now, here we are going to consider, you see, we know standing waves on a line. Standing waves on a line, whenever ZL is not equal to Z0 of a transmission line, so the incident waves are there as well as reflected waves are there on a line, standing waves are there. Now consider a uniform plane wave traveling in, you see here, non-homogeneous medium. Non-homogeneous medium means whatever the characteristics or whatever the properties of the medium are not same. Medium 1 has some properties, medium 2 has some properties, the intrinsic impedances are different, the corresponding relative permittivities and relative permeabilities are different. So we can call it is a non-homogeneous medium. EM wave characteristics 1, we have considered that medium is a linear, homogeneous and isotropic medium. We have assumed like that. We have derived the EM wave equations. Now here we are going to consider the EM wave characteristics to the same electromagnetic wave. Here in this electromagnetic wave, the medium is a non-homogeneous medium. We are going to consider two different mediums at a time. So non-homogeneous media, when uniform plane wave travels from medium to other, having, you see, different intrinsic impedances. We have already discussed about this intrinsic impedance eta. So the reflection takes place, you see, the reflection takes place at the boundary. Suppose first medium intrinsic impedance, second medium intrinsic impedance are not same. So there is a mismatch of impedances. So definitely there is a reflection taking place. Next, the part of the wave transmitted in medium 2. So some part of the wave is reflected, some part of the wave is transmitted, and remaining part is reflected back to medium 1. Depending upon the constitutive parameters of the media, depending upon the manner in which the uniform plane wave is incident at the boundary, there are two cases of incidences. Now you see broadly, already we have discussed the concept of transmission line. The same concept we are going to apply for these non-homogeneous mediums of two different mediums. We are going to consider with different properties. So whenever there is an interface between the two mediums, whenever the electromagnetic wave is incident, suppose whenever the intrinsic impedances are not same, some part of the wave is reflected back, some part of the wave is transmitted to another medium. Now, this incidence, there is a two types of incidence are there. One is a normal incidence, another one is oblique incidence. We are going to discuss about, I am going to explain about this normal incidence. This oblique incidence, you prepare yourself, or you see in YouTube also there is available. You listen YouTube videos, you take one or two classes. This about oblique incidence. Oblique incidence means it makes the incident wave, it makes an angle with the plane of incidence. There is again horizontal polarization and vertical polarization is there. So that oblique incidence derivation part, all things those who are interested to listen, to refer any YouTube videos, you will get. Otherwise, I will search YouTube videos. I will post in our group. You see that YouTube videos for oblique incidence. Now I am going to discuss about in this class this normal incidence. So this normal incidence means here for the boundary interface, whatever the electromagnetic wave that is we are calling incident wave, it is normal to the boundary between the two mediums. So that's why we are going to call it as a normal incidence. Ragesri, when that
సార్ సార్ అర్థమైంది.
now you see here first heading normal incidence yet plane dielectric boundary. Dielectric boundary means here both are dielectrics. It is a one dielectric, it is a another dielectric. So now you see medium one, medium two. In medium one, what are the parameters we are going to consider? Epsilon one, mu one, and sigma one, eta one. For every medium, we need to consider these four parameters. Mu one, epsilon one, sigma one, eta one, and corresponding to medium two, one second. Hello. Epsilon one, mu one, sigma one, eta one. And coming for medium two, epsilon two, mu two, sigma two, eta two. So there is a two different properties, but both are dielectric mediums. Even though it is a dielectric medium, suppose it is a free space, this sigma one is zero. Suppose it is some other perfect dielectric, sigma two is also zero. But suppose there is a practical dielectrics, they offer some conductivity, some amount of conductivity. Okay. Now you observe here, there is an incident wave. That incident wave I am showing. So please, you see first of all this plane. Here the wave is propagating along z direction. The wave is propagating along z direction. Now here I am considering z is equal to 0. At this boundary, it is a z is equal to 0. Now I have considered this boundary interface is x-axis. And there is a y-axis also. That y-axis I am going to show like this dot. So y-axis is there. Y-axis is there. So whenever these three are mutually perpendicular to each other, then only there is a electromagnetic wave is exist in the dielectric field. So electric field is distributed along x direction. Magnetic field is distributed along y direction. Wave is propagating along z direction. Now I am not showing this magnetic field here. Just I am representing there is a electric field is there as well as magnetic field is there. That magnetic field I am representing like a dot with circle. Are you okay? Now, if z is equal to 0, there is a, that's why there is a x, y, z. Now you see here, electric field intensity is there. It is distributed along x direction. That is a I, suffix I indicates that it is a incident wave. Electric field intensity incident wave. And there is a magnetic field intensity is there. That is a HI bar. Magnetic field, incident magnetic field. Because in the AM wave, combination of electric field and magnetic field and wave propagation in z direction. So electric field intensity EI bar, it is showing along x. Magnetic field intensity HI bar, it is showing along y direction. Wave is propagating along z direction. So it is going to be incident at this boundary. It is going to be incident normally. You see this one, the incident, it is an incident wave. It is strikes this boundary surface or interface normally. So whenever it is interface, this striking this is a at this interface between the two boundaries, the intrinsic impedances. The intrinsic impedance of this medium 1 and medium 2 are not same. Intrinsic impedance of medium 1 and medium 2 are not same. Some part of the wave is reflected back. So you see, it is a reflected wave, reflected electric intensity, reflected magnetic intensity, and the wave is propagating in, it is a forward direction, it is a backward direction. And then some part of the wave is transmitted to the second medium. So you can show here T suffix is transmitted wave into second medium and corresponding magnetic field, and the wave is propagating in another direction. That's right. That's
Sir.
right.
Sir. Yes, sir.
Sana.
Yes, sir.
Okay. Are you okay? So there is a EM wave. This EM wave we are showing like this: electric intensity in X direction, magnetic intensity in Y direction, wave is propagating in Y direction. The boundary surface or interface between the two mediums, it is, I am considering it is like X, and wave is propagating in Y direction, and the Y direction is also there. The magnetic field is distributed here. Now in medium 1 there is a two waves. Incident wave is there, reflected wave is there. In medium 2 only one wave, that is the transmitted wave. Okay. Now you consider from the above figure, it is clear that in medium 1 the total field comprises both incident and reflected. Here there is incident wave is there as well as reflected wave is there. So total electric field intensity in this medium, total electric field intensity in this medium, you can write EI bar plus ER bar, incident wave as well as reflected wave. And coming for total magnetic intensity, HI bar is H1 bar mean medium 1 magnetic intensity. H1 bar is equal to HI bar plus HR bar, incident magnetic intensity plus reflected magnetic intensity. Okay na? Now coming for in medium 2, there is a transmitted electric intensity and transmitted magnetic intensity. Now you see E2 bar is equal to, there is only one wave, so only transmitted wave. So E2 bar is equal to ET bar, transmitted electric intensity. H2 bar is equal to, in medium 2 magnetic intensity, H2 bar is equal to HT bar. Okay na? Now already in the first unit we have seen boundary conditions. Whenever the electric field intensity is passing from one medium to another medium, dielectric 1 to dielectric 2, or from dielectric to conductor, we know there is a tangential component or there is a normal component. Suppose it is a tangential component, uh, uh, if the electric field intensity is same in medium 1 and medium 2. So based on that boundary conditions, based on the boundary conditions, you see E1 tangential is equal to E2 tangential. So what does it mean by E1 tangential and E2 tangential here? Electric field intensity tangential component in medium 1, electric field intensity tangential component in medium 2, both are same. Similarly, the magnetic field intensity H1 tangential 1 is equal to H2 tangential. That means that tangential component of medium 1, because whenever both are dielectrics, and tangential components of medium 2 of magnetic intensity are also same. So we equate this electric intensity and magnetic intensity. Now we write EI bar, that is the electric incident electric intensity, and ER bar, reflected electric intensity, is equal to ET bar, transmitted electric intensity. Similarly, coming for magnetic intensity, H1 bar, magnetic intensity, it is not H1 bar, HI bar, incident magnetic intensity plus reflected magnetic intensity is equal to transmitted magnetic intensity. Now we know the relation between electric intensity and magnetic intensity from the previous discussions. So what is the relation between electric intensity and magnetic intensity? Eta is equal to electric intensity by magnetic intensity. So in medium one, you write in medium one, coming for incident wave, EI is equal to eta 1 into HI. Okay, na? Eta 1 is equal to electric intensity instant wave. EI is equal to eta 1 into HI, or eta 1 is equal to EI by HI. It is a one equation, intrinsic impedance. Coming for another intrinsic impedance for reflected wave. Reflected wave means the direction of propagation is opposite to the incident wave. The direction of reflected wave is opposite to the direction of incident wave. So that's why you write that relation ER is equal to reflected electric intensity is equal to minus eta 1 into HR. Are you okay? Ragasri?
Yes, sir.
Okay, la? Okay, now the relation already we
Yes,
know.
sir.
But
Okay.
what is the difference here for positive and negative? Reflected wave is in opposite direction. For that purpose, we are showing there is a minus sign. Coming for medium two, there is only one wave, that is the transmitter wave. So you can write ET bar is equal to eta 2 into, it is because it is the second medium, eta 2 is equal to eta 2 into HT. Okay, na? Now, according to tangential components, we have a relation, this EI bar plus ER bar is equal to ET. Now, we have another one, that is a HI bar plus HR bar is equal to HD bar. Now you substitute this HI here. HI you are going to get HI is equal to EI by eta 1. Next, HR is equal to minus ER by eta 1. So minus ER by eta 1. HT is equal to ET by eta 2. Now here you take here eta 1 is a common. So you will get E1 minus EI minus ER is equal to eta 1 by eta 2 into ET. Okay, na? Is it okay? Now we have the two equations in electric intensity. It is one equation, it is another equation. If you add this equation 1 and 3, if we add this equation 1 and 3, EI plus EI, 2I, ER minus ER gets cancelled. So here ET is a common, 1 plus eta 1 by eta 2. You take LCM for this. So eta 2 plus eta 1 divided by eta 2, that is a 2 into EI is equal to ET. So next, you write this ET is equal to in terms of 2 eta 2 by eta 1 plus eta 2. This is called the ratio of ET by EI, transmission electric intensity to incident electric intensity. The ratio of transmitted wave to incident wave is called a transmission coefficient. You write here the transmission coefficient is denoted by tau. So the tau is defined as the ratio of transmission electromagnetic wave to and transmitted wave to incident wave. So this transmitted wave to incident wave is equal to 2 into eta 2 divided by eta 1 plus eta 2. So it is the formula for transmission coefficient. Now, similarly, if we subtract this one, if we subtract, eliminating or if we eliminate for eliminating this one, just you subtract this one. So from equation 1, if you subtract, definitely this transmission coefficient is eliminated. You see here. ఇది ఎలిమినేట్ చేయాలంటే ఏం చేయాలి? You need to multiply this equation 1 with n1 by n, eta 1 by eta 2. Now, you just, it is a simply modifications. So simply modifications here, or we have this ET, we have a formula. What is this ET? EI plus ER. Okay, we have this formula. ET EI minus ER is equal to this ET is equal to EI plus ER. You substitute that one. Now you substitute this one and you separate the terms. Now you take this EI plus ER is equal to eta 2 by eta 1 EI minus ER. You take EI terms one side, ER terms one side, and you will get EI terms eta 1 minus eta 2 and ER terms eta 1 plus eta 2. So finally, ER is equal to, it is a simply a modification, manipulation part for getting the ratio of reflection to incident wave. So ER is equal to eta 2 minus eta 1 by eta 2 plus eta 1. It is like in our transmission line, ZR minus Z naught by ZR plus Z naught. Here ZR is load and Z naught is line impedance, characteristic impedance. Now similarly, eta 1 is like a characteristic impedance, eta 2 is like a ZL. So the the ratio of reflected wave to incident wave, is equal to eta 2 minus eta 1 divided by eta 1 plus eta 2. Now you see the relation between this reflection coefficient and transmission coefficient. Now if we add 1 plus to this, 1 plus 1 for this, we will get, if we add plus 1, we will get eta 2 plus eta 1, eta 1 gets cancelled, we will get the transmission coefficient. So you know the reflection coefficient is always in between 0 to 1. Already we have seen in transmission lines that concept. Now coming for this reflection coefficient and transmission coefficients of dimensionless, because the ratio of electric intensities, both are electric intensities, and may be complex in nature. According to pointing theorem, we know average power density. Average power density is equal to, already in the previous class we have seen this average power density, P average is equal to half into em square by eta. So you can apply this concept for incident wave, this concept for reflected wave, this concept for transmitted wave. Because incident wave there is a EM wave, in the reflected wave there is a EM wave, in transmitted wave there is a EM wave. So you can substitute PI average. So the PI average means incident average power. Same thing, no issue. Only the incident power, incident wave is in first medium. So you can simply, instead of EM, you write EI square by eta 1. Next, reflected average power density. Here also the reflected wave is in medium 1, so eta 1, and here you can write ER square. And transmitted, so transmitted it is medium 2, you change eta 2 and it is ET square. So based on that, you can write the ratio between average transmitted to average incident. So average transmitted power to average incident power. Now average transmitted power is, half into ET square by eta 2, you substitute, and the average incident power half into EI square by eta 1. Now if you substitute this eta 1 into the numerator, eta 1 by eta 2, half gets cancelled. There is a ET by EI whole square. Already it is a